Okay, so good morning, everybody, and welcome to this talk. Today we have Sima Benstaber with us. She is a PhD student supervised by me and Lloren Serra, and she will talk on trivial versus topological confinement in bilayer, graphene, quantum dots, and rings. Please.
Okay. Hello, thank you for coming to my talk. So today I want to present our work entitled Trivial versus Topological Confinement in Bilayer Graphene Quantum Dots and Ring. So this work has been published in the Journal of Physical Statusology and was chosen as a cover page of the volume of June 2022. So this work, as Mr. David said, was under supervision of Mr. David and Professor Lloren Serra. So firstly, I want to talk about in general introduction about graphene material. So graphene material, as I think almost of you knows graphene, that is just a material composed by carbon atoms in a hexagonal structure. So this material, as you can see here, this is the sheets of graphene monolayer, and it can be composed by two atoms in per unit cell. So we have one atom A and B atoms in the unit cell. So this material, it can be like the base of several structures, as in can be like wrapped up like in 0 dimension, like in fluorine, or enrolled in 1 dimension, like in nanotube, or like sticked in 3 dimension, like in graphite. So we calculate the electronic structure of monolayer graphene was calculated using the type-bending model, and this is the electronic structure of graphene material as represented here. So we have here the valence band and the conduction band, and this material, this electronic structure is as you see here, we have like touch in point. Those points called direct points. We have K and K prime points, and they're presented as a value for graphene material. So from the type-bending model, the Hamiltonian for monolayer near those points is represented as this Hamiltonian here. I don't know if you see the pointer, where VF representing the Fermi velocity, sigma representing the Pauli matrices, and K representing the momentum. So if we do like a zoom in this area here, so we have this structure here. This is one structure near K value, the K value. So in early research of graphene, so graphene is being identified as a very promised material for quantum electronics, like using topological states for quantum computing. And also when we use like in spintronic area, we use like spin degree of freedom as an information tool of carriers. And also the very good things of graphene is that we can use the value degree of freedom also as a tool for information. And this is area of valitronic applications. So our aim of the work is to confine electrons. And electrons in monolayer graphene, it's a little bit difficult because most experimentalists, they use like etching to having the confinement, but it's difficult to find like a single electron. So for that, so it's like for that we study the bilayer graphene material, and this is the aim of our work. And the bilayer graphene material, it is like a good textbook candidate for how one can tune a gap and confine electrons. And this material, as you can see here, is composed just by 2 sheets of graphene. This is the first sheet, and this is the other sheet. Each sheet have 2 atoms. We have A1, B1 for one sheet, and E2, B2 for the other sheet. And gamma 0 here representing just the distance between the 2 atoms, and gamma 1 here representing the interlayer hopping. So the Hamiltonian of bilayer graphene is represented by this Hamiltonian here, where P representing the momentum, Lz representing the magnetic length, tau representing the valley, sigma representing the sublattice, and lambda representing the layer. So the band structure of bilayer graphene is represented at this band structure here, and this is in Brown zone. We have K prime valley and the other valley near K. If we do like a zoom in K here, we have this spectrum, and the spectrum of bilayer graphene in this case is uncapped spectrum. So the things of bilayer graphene is that when we apply a magnetic field, we can tune a gap, so the gap is open when we apply a perpendicular electric field to this bilayer graphene material. So the motivation of our work is to study the electronic confinement in bilayer graphene material. So in this case, I want to discuss the case of wire when we apply like a voltage to the top and the bottom of the bilayer graphene. So the first confinement type is the trivial confinement. This one. And this is when we have like in the top sheet of bilayer graphene, we apply a potential positive, and in the bottom we apply a potential negative. And with difference of potential, we confine the electrons in this white region here. And as a consequence of this type of confinement, when we calculate the energy spectrum of the energy as a function of the momentum, we get like a gap open in the spectrum. In opposite to the other type of confinement. So this type of confinement we call as a topological confinement, and that because we have in the same sheets of graphene, in the two regions, we can apply a different potential. In one region, we have plus potential, and the other one, we have minus, and in the bottom also, we have the opposite. So as a consequence of this type of confinement, we get in the region, I don't know if you see this region here. Oh, sorry. This region here, we have the boundary between the area when the potential change in the sign. In this area, we have the state are propagate along this area when the potential change in the sign. This area we call as a king, and the state we call as a king state that are propagate along this area. So when we calculate the energy spectrum, we found that in the middle of the gap in the middle here of the gap, we get like a topological state that occurs. And for one value go to one direction, and for the other value go to opposite direction. So we get a value momentum locking in this case. For topological confinement, we have two types. We have single king and double king. The double king is just the parallel kings. So we have just as a consequence of this type is we have like 4 branches, extra branches in the spectrum. So for the paper that I want to discuss today, this is the case of a loop when we have a graphene loop, as this loop here. So we apply, this is a topological case when we apply a minus potential inside, and outside we have plus VA. This is here the gray sheets representing the graphene, and the color is representing just the gates applied to the bilayer graphene. So we discussed 4 cases. The first case is when we have like a trivial dot. Trivial dot is just when we have a dot like this, and the radius is 50 nanometer, and we don't have any width, and we apply plus the potential outside, it's 10 millielectron volt, and inside is 0 millielectron volt. And also the second case is the trivial loop when we have outside plus and inside also plus, and we have this width. And this region is there is no potential applied in this region. So this is trivial loop. And here we have 50 nanometer in the width. The third case is topological loops when we have outside plus potential and inside minus, and the radius is 50 nanometer and the width is zero width. And the fourth, it's topological loop. We have minus inside plus outside, and the width is 50 nanometer. So this is the 4 cases that we discussed in the result. So we model this behavior with the 2D quantum model for low energy of bilayer graphene, and we use the Hamiltonian here with, as I said before, that tau representing the value, which value that we used, and sigma representing the sublattice, and lambda representing the layer, and VA here representing the potential applied to the 2 sheets. So we consider potential of circular shape because we discussed now the case of circular like a dot or a ring. So we use this circular formula with VA in representing the inside potential and VA out representing the outside potential. Here the R and W representing the width and the radius, the parameter that we use for in the, and S here representing the diffusivity. So the diffusivity, that means the smoothness of the potential, and we choose 12.5 nanometer value because it's a realistic value that experimentalists can use for the model. In the results, we show here the 4 cases, the 2 for trivial and the 2 for topological. For the trivial one, we calculate for all. I calculate the energy as a function of the radius. In this in this spectrum here, we show for a ring, when we have a width of 50 nanometer, the case of width 50 nanometer, we found that the energy spectrum is opening a gap, as you can see here. And this is just due to the energy quantization by the width of W50 nanometer. And if you see in the topological dot, in the trivial dot, we if the radius is increasing, we get that the gap it's closed with the radius big. So if we have a small dot, we get in the spectrum a very large gap. In opposite to the topological one, here in the ring, here the topological, but in this case with a finite width. In this case, we found that the behavior is different from the trivial one, and we get a crossing in zero energy, as you can see here. But we have this behavior here. We have horizontal branches that is similar to the ring, to the trivial ring, but with the topological character, we get the state in the middle of the gap. But for the topological ring with zero width, we found a regular branches or the branches, and then the quantization is that we can explain by quantization of a rule of 1D closed orbits, similar to both Sommerfeld one. Now I want to talk the effect of magnetic. Yes.
Over
here.
Right. Yes.
This is ring with zero with. Yeah, because they are all topological loops. Yeah. Okay, so now I want to go to the magnetic field effect. So as we know that electrons in the bulk shows emergence of discrete Landau levels with energy, and the energy satisfies the following conditions. So this condition here where omega is the cyclotron and L representing the levels. So we want to know if this condition is fulfilled when we apply magnetic field to those cases. So this is the trivial case. Here, this is the loop, and this is the dot, the ring of the dot. And here I use the same width, but different radius. So here I have a very large radius with 50 nanometer, and here 10 nanometer. So as a consequence, we found that in the large R, we found like a very good, a clean branches that can, and easily we can see that the condition of Landau level is satisfied in this case. And but in the dot, we also have the condition of Landau levels, but the spectrum shows not very good clean emergence of Landau levels. Because I think we use a little bit of filtering, we use a technique in our numerical calculation, we use some filtering, so maybe because of that we get this behavior, but otherwise we have the Landau levels physics satisfy in this case. And why we get here this condition, because Landau levels requires a 2D region of potentials, so where the electron's motion is locally free. So here also, when the magnetic field is increased almost to go to the very large Tesla, we get the very large gap that opens here. The case of topological loops, we get another behavior. It's different from the trivial one. As you can see that for the ring with zero width, we get like a sequence of branches. And this is there is no sign of Landau levels physics because of 1D loop. But if you go to the other one with the finite width, we get the two behaviors. We have the sequence of branches and also the emergence of Landau levels in the higher energies. So as I said, the topological rings with finite width shows both parallel branches and also symmetry of Landau level discretization. So as a conclusion, we discussed two types of confinement in binary graphene structures and used by top and bottom gating, trivial and topological one. And also we find some differences in the energy spectrum for the dot and for the rings. And our numerical calculation suggests that magnetic spectrum of both confinement type will be detected using the experimentalist techniques, which will represent a significant step toward topological quantum computation in graphene systems. And this is some references about our paper that talking about topological and trivial confinement in Bilayer graphene. And thank you for your attention. I think I go fast.
Thank you. So now time for questions, discussion, remarks, criticism. Misha, please.
We tested states that are 80 states. We tested states inside. So we have single electrons, yeah.
For each state. For each state, how many states?
So we have doublet. When we diagonalize the Hamiltonian, we get like 2 eigenvalues in the system. So we have like 2 per state, because we have this chiral behavior.
Yeah, but how many states do you have? For instance, if you show the spectrum,
yeah, the other.
For the dot, oh no, this one, no, no. If you let's say, can you show the energy spectrum?
Okay,
yeah, this one, for instance, for the dot, right? So let's say for a given radius, how many states did you consider?
It's for all the calculation, I consider 80 states.
80.
Yes.
Okay.
And then when we have like a cutoff, we can just have many states.
How many of these 80 states are divided?
How many?
How many divided?
How many by?
I mean, how do you fill these states with electrons? I mean, you have the states, and then you have to put electrons here. How do you fill these states?
Yeah, I didn't do this work about the filling of states, so I just do like a theoretically. Okay.
Sorry, Misha. Sorry. Here, the Fermi energy is taken here at 0. This is the Fermi energy.
Yeah.
So in principle, all these states below Fermi energy are occupied. Okay, and then those states are empty.
Yeah, here, yeah.
Well,
so only one state.
But there are more states here below.
Below.
I mean, all these branches just over
because
this.
we are interested.
I mean, because
in the low energy, yeah. Because of that, so I do this cut just to focus on the low energy.
Yes. Yeah, and this is because the graphene spectrum is not bounded from below, and so essentially you can have infinite number of electrons. Of course, this is a limitation of the model of the Hamiltonian that we use. Why the normal metal you have just a few states, and here you have many of them.
But this is a particularity of graphene. So maybe because the thin behavior of the thin sheets of graphene is different from the other metals.
When you find different preparation, plus and minus, is there any card for? Because here you can form, here you can electron.
When you have plus and minus, and then the electrons, yes, it's right, pass, and there is no column blockings in this case. I neglect the column blockings.
No, but I think Misha is asking if you can show the system, the setup. You see here, no. No, the other slide.
Yeah.
Here you have positive.
Yeah.
You have negative.
Yes. And this
So in principle, you have positive, negative. One would expect a current of electrons, a flow of electrons going from here to here to here from here. So this is the question, right?
Yeah. So you mean I should calculate the scattering of the electrons in this case? Yeah. Yeah, we do that, but with our previous work, but just in the wire case. So I didn't do it for the loop. So I can just tune the current here, and maybe I can have like the conductance. So
no, these are gate potentials. So those regions ideally are isolated. So you cannot have electrons going from here to here. Take this as an infinite. On the upper case. Yeah. Well, this is what Nassima explained. What you have here is they call it a King state. So electrons circulating around.
Yeah.
Okay.
In the region.
In the region of the dot. No, actually, this is better seen if you go back to the slide, the one that you show.
After the wire.
Let's try that. Yeah, here.
Yeah,
here, this one. Maybe you can explain this a little bit better.
So here we have this area of minus and plus, and this region here. This is the region where the state are propagate around this region. So they cannot electrons. It's like like an obstacle this area. So the electrons just propagate along this area. So we cannot transfer to the other region.
So any other question? So I have one myself. When you show the spectrum as a function of magnetic field, I would expect symmetry. When you invert the magnetic field, the energy is not the same, right? So why do you have this?
Okay.
Here, for instance, the Landau levels.
Yeah.
When you change the magnetic field, the Landau levels do not change. But here, what happens when you invert the sign of the magnetic field?
The gap is going to the other side. So
Do you have a physical explanation for this?
Actually, so because I'm interested just in this area when I found like a physics explanation of Landau levels.
Yeah, but I mean, can you see some connection between this level at, let's say, 2 Tesla
yes.
and the same levels at -2 Tesla? Are those the same?
Yes, but it's like with the reversal of the sign. Yes.
So the energy changes sign.
Yeah.
When you
So
change
it's like
magnetic,
minus 0 point something, and there we have it.
and there is some physical principle behind
like
this.
Chiral symmetry.
Chiral symmetry.
Yeah, we also have this. The chiral symmetry. Yeah.
Mm-hmm.
Yeah. Yeah. In our study, we removed like the spin. We neglected the spin degree freedom. Yeah. We are just interested in valid degree freedom. Valid tracks.
Yeah, the spin does not enter the Hamiltonian. Mm-hmm.
Yeah.
Yeah, here there is no, the Zeeman interaction is not taken into account. These are orbital effects. Yeah.
And this is our perspective work for the future.
Can you explain this chiral symmetry
yeah,
better?
I can explain it in the wire case. Okay, here as an example here as you show here. So for the state below here we have like minus state, and here we have like plus state. So the states are coming in doublet. So because of that we have this chiral symmetry. And also
And
for
in the topological case, what happens?
it's the same. Also for the topological case, you have again the chiral symmetry.
Okay, so let's stop here. So thank you, Nasima.
Thank you.
Is there-
Thank you.
Thank you.